In this video, we're going to look at what the meaning of an antiderivative is. So let's start with a simple question here. Suppose we know that the derivative of some function is 8. Can you figure out what such function has a derivative of 8? Well, with your knowledge of derivatives, hopefully, you can guess, okay, that g of x could possibly be 8x. Right, because the derivative of 8x is 8. Okay, and that's one solution, but there's actually more. What about 8x plus 2? Right, the derivative of 2 is 0, so still the derivative of 8x plus 2 is also just 8. You could have 8x minus 10, 8x plus 11.5, 8x plus pi. 8x plus or minus any constant has a derivative of 8. Okay, so what we're doing is we're going backwards. Given a derivative, can we find the function? And that's what antiderivatives are about. They're about going backwards. Okay, what about 3x squared? Actually, that should say f prime of x is 3x squared. What if the derivative of f is 3x squared? What is f of x? Okay, hopefully you've done enough derivatives to recognize that the function whose derivative is 3x squared is x cubed, because we bring the 3 down up front, we reduce the power by 1. Okay, but obviously we don't want to compute every derivative by guessing and checking, so there are a number of antiderivative rules that will help us out here. Okay, so first let's define an antiderivative. So if capital F and little f are two functions such that the derivative of capital F equals little f, then capital F is called an antiderivative of little f. Okay, and because the derivative of any constant is 0, and I could have put, constant over here as well, the derivative of that is still 3x squared, every function actually has infinitely many antiderivatives. So f of x plus, we're just going to use c, where c is any constant, represents the infinitely many antiderivatives, or the family of antiderivatives of f, of little f. Okay, which brings us to indefinite integrals. We need a better notation system. So let's suppose that capital F is one of those infinitely many members of the family of antiderivatives of little f. Then the way it's more commonly written is with what's called an integral symbol, and you read it the antiderivative of little f of x, and then we put a dx equals capital F of x plus c. So this is read the antiderivative, or sometimes it's read the integral of little f of x dx equals capital F of x plus c. So the symbol right here means we're going backwards, we're anti-differentiating. The dx does have a meaning, and it has to do with definite integrals and area. It can be explained that way. But as far as we're concerned right now, what the dx does is two things. It tells us that's the end of the integral. Stop here, okay? And then whatever's after the dx is separate from the indefinite integral. It also tells us the variable that we're working with. So if this had said dt, my function would need to be in terms of t, or we would be anti-differentiating with respect to t. Okay, so c is an arbitrary constant. Okay, this part, the antiderivative of little f of x dx, it's called the indefinite integral. Or antiderivative. Let's make some more space here. Okay. Whatever is inside that integral is called the integrand. Some terminology for you. That part right there is called the integrand. And the c is an arbitrary constant. It's also sometimes called, let's add this in here, the constant of integration. I can squeeze it in there. It's also called the constant of integration. And one more terminology for you. The dx is called the differential. Okay. Guess we didn't need more space there. So using this notation, let's go rewrite the results from up here. Okay, so using this new notation, we can say the antiderivative of 8 dx is 8x plus c. Or over here we can say the antiderivative of 3x squared dx is x cubed plus c.